Hi everyone, welcome to our talk. My name is Vincent, and together with my former colleague Matthijs, I'll be talking to you about this thing called fairness in algorithms, which is an important topic. In particular, what we're going to talk about is how priors can be this amazing potential for fairness. But in order to get there, I would like to tell the story of how we ended up writing this blog post. It's a bit of a longer story, and if we're going to build the model, it does it justice to also explain how we got there. Because it kind of started with this observation. My background is in operations research, so very typically what you would do is you would think of these constrained systems that you're trying to optimize. So let's say that we're doing a portfolio maximization. So you would do something like, hey, I want to maximize the profit of my portfolio X, which is some return for, let's say, stock 1 plus some return for, let's say, stock 2, and we do that all the way up until some stock K. Like, this is something you could go ahead and optimize. And this would be kind of silly. Like, you wouldn't optimize a stock portfolio this way, because this is an incomplete description of the problem you're interested in. You're not interested in calculating the max profit you can get with a portfolio. You're interested in finding one that is subject to, at the very least, your budget. You're going to invest parts of your budget in these different stocks, and you cannot invest more than what you currently already own. So if I were to say, hey, let's just maximize without this constraint, I would be calculating a silly thing. But you can go a step further. It's not just this budget that we have a constraint for. You can also say, well, we have this risk preference. You know, the more risky the bond, the more return you'll get, but you also get more risk. So there's a risk appetite you got to keep in mind here as well. And back when I was in college doing operations research stuff, I would be focusing on problems like this. And one of the core lessons you learn is, sure, you want to optimize this, but you're doing something really silly if you don't have these constraints in mind. And these constraints really matter. Sure, I would get a higher profit if I didn't use them, but that's beside the point. I don't care about having a higher profit, I care about solving an actual problem, and actual problems tend to have these constraints. Now, college has been a while, I've been in industry, been doing data science for a bit, but one thing I've noticed is that most of the machine learning models that people typically think of and that they apply, they tend to optimize something called a loss, which is this bit. They really try to get like the maximum accuracy, and this is typically what models are judged on. But I haven't seen a whole lot of models do this. And the more and more you start looking at how these models are applied, the more and more this actually becomes kind of a concern. Because if you think about everything that could go wrong with a model, sure, the accuracy can be too low, that's a valid concern, but it's certainly not the only one. And I think it would be much more interesting if we start thinking about what sort of constraints we can come up with our models in order to make the applications better. And I think I can make the point here that just like before, maybe I don't care about getting the maximum accuracy as much because I'm interested not in the model, rather the application of it. So these constraints really, really matter. And there's one particular constraint that Matthijs and I were concerned with when we were writing this blog post. So let's write everything down now, a little bit more in machine learning terms, a little bit less operations research, and a little bit more terms of machine learning. Let's say that the task that I'm trying to achieve in machine learning here is that I'm trying to minimize some sort of loss. There can be mean squared error or something like that. But when you're minimizing such a loss, then let's say that I have my machine learning function and there's these parameters theta that I'm trying to optimize given some sort of training data x that I'm trying to minimize towards those parameters theta, and I've got my y's, which represent what I want to predict. These are the typical mathematical hieroglyphics that people like to write down. So, fine, let's be open-minded to what this function f could be. It could be a neural network or a linear regression. But what I'm interested in solving now is getting the best values for theta, but now I'm also going to add some sort of constraints. Something that says subject to. And one thing that might be cool to do here is to say, well, I'm interested in a very accurate model, but I would like the model to be at least fair. And it should be said, there are many ways of defining fairness, and I'll keep it vague for now. But you could say that it should at least be something of a constraint. You could say, well, the fairness with regards to, let's say, gender, that has to be higher than at least some sort of threshold, a threshold for the gender fairness that I want to have. And I can immediately imagine many use cases where you'd have to do this by law. If you're going to make an automated decision whether or not someone is supposed to get a job based on a resume, then if you're deploying a system without such a constraint, I would have a hard time convincing a lawyer that you're doing it the fair way. Another thing that you can do is you can also consider something like race, perhaps, if that's available. And you can maybe also consider something like, well, maybe we also want to be fair with regards to location. There's something to be said that for certain decisions, it shouldn't matter in what zip code you live. But the idea is that at least now we've got some idea of how we might construct a machine learning model that can behave somewhat fairly. It's just that we got to start thinking about how we are going to, solve the numerical aspect of what fairness is. We got to have a small talk about that. And there are many different ways of defining this. But what Matthijs and I did is we didn't come up with our own way of doing this. Instead, we actually started reading this paper. In particular, the name of the paper is Fairness Constraints, Mechanisms for Fair Classification. And I hope I'm pronouncing the names correctly, but it's written by Zafar, Valera, Rodriguez, and Gumadi from the Max Planck Institute of Software Systems in Germany. But we found a paper that actually describes a mechanism that does exactly this. And this paper also mentions a way to quantify this fairness. And here's the main idea behind the mechanism. What you can do is you can calculate the covariance between a sensitive attribute and the distance to a decision boundary. So just for emphasis, Z here represents a sensitive attribute. And that could be, for example, gender, right? That's a sensitive attribute. That's a column in your data set that we would like to be fair against. And what we're going to do is we're going to also compare that against the distance to the decision boundary. And the paper says, well, we can approximate that. And what we can then demand is that this covariance is bounded, that we're not going to overshoot there. We don't want our sensitive attribute to correlate with distance to the decision boundary. If the covariance is large, then the decision boundary will depend a lot on a sensitive attribute. And by saying that this covariance has to be bounded, you have a way to quantify this unfairness. So what I can do is I can erase this. And I can copy this. And I can say that this has to be smaller than or equal to a certain threshold. And this has to be larger than or equal to minus that threshold. And we have to do this for every sensitive attribute. That's the idea. And if we then assume that this is a logistic regression, then this whole entire system has a nice property, and that is that as far as operations research algorithms are concerned, this is convex. Most of the parts are fairly linear, and that means that we have an algorithm that can solve this with a guarantee for optimality. So this got us kind of excited. It's not everything. I mean, it's just logistic regression. But with logistic regression, you can already do quite a bit. And another nice aspect of this is that we can also have variants of this. We can say, well, let's calculate this covariance, but only limit ourselves to points with a positive label, so to say. That's something that we can also go ahead and do. But the main thing, at least to us at the time, was, hey, this is cool. Let's write an implementation for this. And I would like to say we did it, but Matthijs actually wrote most of it. So Matthijs and I were in this phase that we wanted to have a place where some of these fairness algorithms could go. So we made this open source package called scikit-lego. There are some filtering tools that you can use, but Matthijs wrote this. So scikit-lego supports a couple of algorithms that do this. And this was interesting to us because we could then start trying out to benchmark things with this. So what I'm going to do now is I'm going to give you a small demo, just to get a feel of the numerical mechanics that are at play here. That also means that we're not doing PyMC3 just yet, we'll get to that in a later bit, but I do feel it's nice to get more of an intuition behind what's happening. So what I'm doing now is I'm going to this website that, full disclaimer, I made. It's called drawdata.xyz, and the whole point of the website is that you can quite literally draw yourself a dataset. So what I'm going to do is I'm going to draw me a classification dataset, so to say. So let's just pretend that we have a couple of points over here that are all from class A, and let's then also say that we've got some other points, maybe class B, a little bit more below here. Let's do something like this. This is our dataset that we're going to go ahead and play with. And what I can go ahead and do now is I can go ahead and click this copy CSV button, and that will allow me to use the read clipboard command from a Jupyter notebook, and that means that we can just go ahead and use this dataset in a notebook. Okay, so I'm in a Jupyter notebook now, and Pandas has this lovely read clipboard function, which I can just go ahead and use. So I'll read in the dataset that I just drew via the clipboard into this notebook, and I should now have a data frame available that I can go ahead and draw. And this is a dataset that I can now go ahead and use, and let's say that this is our classification dataset. This is what we're going to classify. We're going to have some sort of a logistical regression that's going to separate the two classes out for us. And that's probably going to mean that we're going to get something of a line here where the algorithm's going to say, everything on this side that's yellow and everything on this side that's purple. And, the line might not be exactly there, but somewhere around there. And that can be your algorithm. But now let's say that we also want to have this fairness thing being applied here. It might be that there is a subgroup here, and it'd be a shame if that subgroup suddenly correlates with this decision boundary, so to say. But let's now say that we've got a sensitive attribute, be it gender or anything else. And let's say that that sensitive attribute splits this data set up into two segments. So let's say that this here is one of those segments. You're either in the segment or you're outside of it. But if I were now to look at this segment and at our decision boundary, then I hope you would agree that this is a little bit wary. And that's because this separating line is almost making the exact same separation as this sensitive attribute might. So what I'm going to do now is I'm going to add this information, this subgroup, to our dataset, and then we're going to use the, so to say, fair model that's in scikit-lego to see if we can tune it in a way that we like. To get this data in, though, what I'm going to do is I'm going to use another package, again, full disclaimer, it's something that I wrote, called human learn. And I'm using an alpha version right now. But what it allows me to do effectively is it allows me to say, well, there's a data frame, and I would like to be able to make charts using that data frame. A chart like this one. And you can see that this is the alpha version because there is some text here that you can pretty much ignore. But the idea is we get this chart that we can draw something on. And if I were to look up here, you might notice a similar shape. So it's this data set over here that is being drawn down below here. And before I said I was going to draw something that kind of looks like this. So what I'm going to do now is I'll draw a polygon that sort of looks like that. So some sort of shape. Let's do something like this. Okay, and what I can do is I can just move that a little bit more so that points actually fall under it. Let's maybe make it just a bit bigger, like so. All right. Let's say that that's my definition of my subgroup. So you're either in this subgroup or you're outside of it, and whether or not you're in the subgroup, that is my sensitive attribute. I would not want my predictions to correlate with that. Then what human learn allows me to do is it allows me to take this charts object that I have, which in turn contains this polygon over here, and that will then allow me to make this interactive preprocessor, which is this scikit-learn compatible tool to add features. But in our case, we are just going to use it to add our features to the data frame, the one that we copied in earlier. And just for good measure, just so you can see, we have our label column, that's what we want to predict, and we now also have a sensitive attribute, and that is something that we do not want to correlate on with our predictions. And we also have our x and our y value. And what I can do now is just make a quick plot. All right. And looking at this, I hope you would agree that the separating line we'd have over here is a little bit too similar to the separating line we might have over here. So that's something that we are a bit wary of, so to say. What we are going to do now, though, is we are going to apply a logistic regression, but one that has this constraint attached. And in scikit-lego, there are two such implementations at the moment. We have a demographic parity classifier and an equal opportunity classifier. They're in large parts similar. There's like subtle differences between the two. But for now, what I'm interested in showing you is that when we have a data set here that has a sensitive attribute, one that we can pass along to the classifier, we are also able to say, well, there's this covariance threshold that I want to play with. And what I would like to show is just the effect that you might get on the predictions if we change this covariance threshold. So I can go ahead and run this now. And then we see some predictions coming out. Just for good measure, I think it would be useful to show all of the charts. So I'll just go ahead and add that. So here's what it looks like if I have a covariance threshold that is relatively low. All right, so the covariance threshold is 0.1 over here. And then we see that, you know, it's certainly not this line, right? But it's separating things out like so. What I can do, though, is I can say, well, let's allow for a higher covariance. And when we allow for a reasonably high covariance, then you'll notice that, you know, the separating line that will be optimal, the one that would basically ignore the fairness, well, that's kind of the one you get. However, if I were now to say, well, the covariance threshold now, it's got to be like super low. Like we barely allow for any covariance now. Then what you see is that the decision boundary changes, and it kind of becomes, if you squint your eyes a bit, this separating line here is almost orthogonal to the separating line of the sensitive attribute. And a logistic regression is, of course, something of a linear system, so the fact that we see this isn't too surprising. But one thing that is kind of nice about this way of working is that effectively we get this tuning knob, where we can say, well, I want to have a little bit more accuracy or I want to have a little bit more fairness, and this parameter effectively allows us to balance the two out. So I hope you think that this is indeed reasonably interesting. It's nice to have a button and a parameter for this, but we do need to be careful for a couple of reasons. Like if I'm going to take a step back and just think about this practically, right? For starters, in order to do something like this, you will need to have access to this sensitive attribute. And in many use cases in practice, you might not have the gender or the race information, let's say from a person, so then you can't always use it in a predictive modeling setting. In order to correct for bias along an axis, you need to have the access to the axis. So that is the first thing to keep in mind here. The second thing to also keep in mind is that this is but one measure of fairness, a rather theoretical one at that. And although I think it's noble to sort of investigate this, I don't want to suggest that this is a solution or anything like that. At best, this is a remedy. I think it's a remedy that's worth pursuing, But I don't want to give the impression that this is perfect in any way or form. When thinking about themes of fairness, there are many different ways of measuring that, and perhaps a more important thing isn't to look at the quantitative aspects of this system when it comes to fairness, but in reality we should probably focus more on the qualitative aspects. Themes like, are we open with our model? Can people give us feedback on the model? How do we make these improvements? And how can we make sure that the results are interpretable? Those things aren't necessarily merely quantitative problems. Still, going back to this now though, I do hope that we appreciate that we have a tool at our disposal that allows us to play a little bit with fairness, and that's useful. So you have to imagine that we had this method and then we got curious and we wanted to start benchmarking it. So one thing that we've done is we've taken the load Boston dataset, which if you're using it in your classes, consider a different dataset. There's serious issues with it. But we took that dataset to get an impression of what this control mechanic could be like. So we made a couple of charts as a comparison. What you see on the left-hand side here is a score that we use for fairness. It is the P% score. And the way that score works is you can say, well, the P% score, that's the minimum of the probability of getting a positive label prediction, given that the value for a sensitive attribute is 1, so to say, over the probability that you get a positive label attached, but that you have a sensitive attribute value of 0. The idea being here is that both of these quantities should be equally big. So the odds ratio, if this is a completely fair model, should be really close to 1. However, it's not just this ratio that we care about, we also care about this one. It's pretty much the same ratio, except here we've got a 0 on the bottom, and here we've got a 0 on top. We've just flipped the two. But this is a measure for fairness, and we can see that as we have a higher covariance threshold, that we then get less and less fairness, so to say, as we move. The accuracy on the other side seems to increase when we up this covariance threshold. And that means that we can pretty much now sort of select a covariance threshold where we have an acceptable fairness, and then we still get, let's say, the most accurate model given this fairness constraint. So, if nothing else, on the classification version of the load Boston dataset, we seem to be able to have this tuning knob, so we were relatively content when we were doing this, but something was bothering us when we were thinking about this, and it kind of has to do with this. Let's think about the problem that we're solving if we're doing this, right? We have some sort of a function here that represents a model, and then we have some sort of constraint here. But if I think about all the possible constraints that I might want to come up with, then I'm going to hit a numerical issue the moment that I define this in a non-linear way. The reason why this system is convex is because these constraints behave fairly linearly. But maybe I want to describe my fairness in a way that's not linear. And currently I don't have the methods of doing that. And the same issue applies with this F over here. Logistic regression is great and all, but if you have a very specific model that's very specific to your use case, it might not be logistic, it might be something that's more hierarchical. And if I think about the way that I want people to model, I would really like people to have a very custom model for their custom use case. And the issue with scikit-learn is that it's a little bit one size fits all. So it's great that we have this for scikit-learn because many people will use it, but it's perhaps not going to be really bespoke. We kind of need a different way of thinking about models, actually. And then sort of a funny thing happened, because I remember Matthijs and I, we were standing next to a whiteboard, and at some point we wrote down something along the lines of, we kind of want to have a model, and that model, that's really supposed to be like lessons from data, times whatever constraints that we can come up with. Like, it'd be nice if we can maybe think about it this way. And then we stared at it, and kind of wondered, hey, hang on there. People typically write this down for stuff that you learn from data. And, a constraint, it's kind of like a prior if you think about it. With a prior, you can say what should or should not happen, even if you haven't seen any data yet. And if you can describe fairness in this way as a prior, numerically, you could say, well, that's also a constraint. If you can come up with an appropriate prior, then we can just use proper sampler methods and we get a whole lot of flexibility in return. We can also customize whatever function we've got here. So by thinking about what aspect we want to have in our model when it comes to fairness, we thought it was actually kind of cute. We immediately found ourselves back into Bayes' rule. But in order to do this well, we essentially said, you know what? Let's try to do this in PyMC3. Let's actually try to define a prior that we can use as a fairness tool. Like, instead of having this knob that we can tune with this covariance constraint, let's just have an actual prior that we can give the model instead. So the idea is to construct a fairness prior and to look at the problem that way. So to us, this is a really exciting exercise. However, before you actually go and implement something, it does help if you can at least compare. So our plan at this point in time was, let's take a data set, then we will benchmark it using the tools we made for scikit-lego, and then compare it with a similar implementation, but in PyMC3. And again, the goal is to explore if this whole idea even works. Before we can move on there, though, one thing that is nice to do, at least for us now, is to talk about the dataset that we'll be using to do this benchmark. So the dataset that we eventually chose to use for this benchmark is the arrests dataset. We have a load arrests function inside of scikit-lego, but this dataset represents arrests that were made in Toronto for marijuana possession. The variable that we're interested in predicting is this one. It's the whether or not you were eventually released. And we have a couple of variables at our disposal that we consider sensitive. In particular, that will be your skin color, your gender, and your age. And what we do is we make these variables discrete. So age is now true or false, sex is now true or false, and so is your color. And we consider these the sensitive properties. We would not want our predictions to correlate with these variables. And all the other variables we just keep as is for now. You could still have a pretty good discussion, by the way, on whether or not you're employed and or whether or not you are a citizen, if those need to be sensitive, and that'd be a good discussion. For our intents, though, we're a little bit more curious about benchmarking for now. So for now, that means that we will put those variables into the model, but definitely valid discussion to be had there. And next up, what we did is we made a standard model with scikit-learn, and we made a what we will call fair model. Again, using the same method as before. And when you have a look at the standard model, we have some coefficients that we see, and when we make the fair model, we see that we have different coefficients. And one thing to observe here is that the coefficients of the variables themselves, they change, but not as much as the, so to say, intercept of the logistic regression. And that's a more significant change that we see. So the threshold seems to move more. That's the main difference that we see when comparing these two models. So, okay, interesting. We have a benchmark, we have a data set. That means that now we finally get to talk about PyMC3 at a PyMC3 conference. And this part will be handled by Matthijs.
Right, so the first thing that we actually set out to do was try and recreate the results we had in scikit-learn in PyMC3 as well for our baseline models. So what I've got here is a Jupyter notebook with the same dataset that Vincent had just loaded, except with the fact that these are, like, some of the variables are also scaled to make the modeling process slightly easier. And what I'm going to do here is build up a basic structure of how we're going to compare these models and how we're going to efficiently run some experiments as well. And I'll start with the most basic logistic regression that we tried in scikit-learn in PyMC3 as well. So let's start with actually importing PyMC3. And what I'll do is I'll write a function called benchmark model, which takes a data frame, and this function will actually run, like, define the model that we want to run. So I'll open a model context in here. as model. And inside this model context, I'll go and build our actual PyMC. And with these models, I like to start bottom up. So we first start with the observed data. And in this case, our observed data is a binary variable. It's whether someone got released or not in a certain check. So that means that it's probably drawn from like a Bernoulli distribution. And we'll call this Bernoulli distribution released. And it has one parameter, which is the probability of being released, P. And this is the parameter that we're going to be basing off of our data and our parameters that we'll learn. The data is observed, like the released attribute is observed, and that's actually where what the model will sort of fit on. And this comes from the data frame that we passed in from the released column. The P variable, though, doesn't come out of nowhere. We need to define it. And because it's the parameter for a Bernoulli distribution, it has to be between 0 and 1. And the nicest way to do that is to pass some kind of function through a sigmoid, because a sigmoid is always between 0 and 1. And the thing that we're actually passing through the sigmoid is going to be some learned intercept plus the dot product between our data, x, and some set of learned weights. And this intercept we want to learn, so we put a prior on it. In this case, I'm putting a normally distributed prior on it with standard deviation, or with mean 0 and standard deviation 1. And I'll do something similar for the weights, except that we don't want to fit only a single weight. We want to fit like the amount of columns that we have in our data. We want to fit that many independent weights. And this is what this shape parameter here does for us. So something we don't actually have yet is this x variable, which represents our data. And that's going to be the columns that we selected to be in our model, which was the year column, the checks column, the employed column, and the citizen column. And let's just for good measure make that a NumPy array. When the model is defined and we have our data, what we can do is we can sample from its posterior with pm.sample. And we'll give it like 2000 tuning steps and maybe 1000 draws on 6 chains. What I now like to do is inside this benchmark model function also create a predict function. Because this predict function has access to the scope of the benchmark model function, it also has access to the trace that we fitted in there. So we're going to do something very similar to define like what is the data that we actually want to predict on in here. And we can basically recreate our predict function, so that's this bit, inside this predict method inside the benchmark model here. So let's import from SciPy special the xbit function, which is the SciPy name for the sigmoid. And we'll do something very similar to what we did down in our model. So we'll take the intercept out of our trace, and we'll add to that the dot product of the weights with our x data frame. So this is going to be a 2-dimensional variable, namely number of samples by the number of observations, while the intercept is only 1-dimensional, the number of samples in our trace. So just adding them together like this won't actually work. But the neat thing is that in this case, what we want is that this intercept just gets applied to all our observations. So if we just add a single, like an extra dimensional entry to this first array to make it, in this case, 6000 by 1, rather than just a vector of size 6000, it broadcasts nicely with this 6000 by n observations matrix that we have here. Because the actual metrics that we're going to be using really like just having a single prediction per observation, what we'll do here is just take the average of all our predictions and return that as the predicted probability. In the bottom of our benchmark model function, we can return the actual model, the PyMC model that we made, the trace that corresponds to it, and the predict function that we can use to actually make new predictions based off of this. Because we're now going to run multiple of these models and compare them, it's also nice to just make an actual benchmark function that we can pass a model into and see in a consistent way what the results will be. So this benchmark function will take two arguments, the model that we want to benchmark and the data that we want to benchmark it on. And the first thing that we want to do is split this into a train set and a test set, because we don't want to compute the metrics on the same data that we also use to fit the model. And to do this, we'll use the train test split function out of scikit-learn, and we can import that from scikit-learn model selection. Import train test split. There's some other imports that we're going to need, so let's just get them over with as well. We want to use certain metrics from scikit-learn, most likely the accuracy score, the precision score, and the recall score. And we have a module called metrics here, from which we want to import the demographic parity score, which is the same p% score that Vincent talked about earlier. Right, so after making our train test split, the first thing that we're going to do is actually run the model on our DF train. And out of this comes let's call this a model function. Because out of this model function comes the actual model, the trace, and some kind of predictor function. And to then make predictions, we can define this y-hat proba to be whatever comes out of our predictor when we run that on df test. And the actual predicted class is then going to be whenever y-hat proba is bigger than 0.5, we'll say that someone is released and otherwise they aren't. Something that we can also do here is plot our trace plot, because it's probably something that we want to look at to make sure that our sampling process actually worked as we expected. So let's open up the model context again and run pm.traceplot of our trace. And then all that's left is actually printing the metrics. So that's going to be the accuracy, which is the accuracy score of our df test released versus our y-hat. Something very similar for the precision and the recall, but then we'll use the precision score and the recall score. And we have our actual fairness metric, which was this demographic parity, which works in very much the same way. Demparse score. It takes the true y value, the predicted y value, but then also the column that we actually want to compute our fairness on. And let's put this, for example, on the color column. Call this demographic parity color as well. Right, and if all of this works, we can run our benchmark on our benchmark model with the data frame that we want to fit on. If we then go to look at the results after this is done sampling, we see something quite interesting happen. First of all, our trace seems to have worked fine, right? Our traces look fine. Nice fuzzy worms, no flat areas. We don't get any warnings about divergences or low number of effective samples, and those are all good indications that we were able to explore the posterior space pretty well. But if we look at the actual parameters, they don't seem anywhere near to the scikit-learn model that we had before. And if we look at the metrics, it seems as if this model was already actually extremely fair. And there's nothing really that would indicate such a huge shift between the scikit-learn version of the model and the PyMC version of the model, because they should actually produce relatively similar results. And there's actually already a slight hint here what's happening. because our accuracy and our precision are about 80%, but the recall is very close to 100%. And recall close to 100% could be some kind of indication that actually all our predictions are just going to be 1. Like we're predicting that everyone gets released. And if we look at the data set, that actually might make sense. So if we do a value count on the released column, we see that there is quite a big imbalance in our data set. So by just predicting that everyone gets released, we get a reasonable score out of the model. And because everyone gets released, the model was actually also quite fair. So what is then the difference with the scikit-learn version of the model? The scikit-learn version of our model used class weights to make sure that it wouldn't just predict once for everything. Basically what that does is it says each entry with a released result becomes slightly less important than entries and observations that are not released, to make sure that the overall weighted sum of the released column is about 0.5 rather than like 0.8, which it is now. And we can build such a balanced version of the model in PyMC3 as well. And to do that, let's actually start with copying our benchmark model and calling it balanced model. So making our data, like our model balanced, starts with actually figuring out what the weights for each observation should be. And we'll do that by making a variable called class weights. And this class weights is going to take the value count of our released column, but it's actually going to first take the length of our data frame and divide it by it. That will give us for released, for non-released, a weight that each observation should have. To actually then get sample weights for each individual observation, what we can do is we can take the released column and map these class weights onto them. And this will provide us a vector of the size, of the length of our data set. And we can use that later on in the modeling process to weigh each individual sample. So PyMC3 doesn't have something like a sample weights on this Bernoulli distribution where we can say, please weigh some of the observed data more heavily than others when computing the likelihood of a sample. Instead, we're going to have to do something slightly different. We're going to have to add an arbitrary likelihood term to our model that doesn't stem directly from this Bernoulli observed data. So this line is going to have to go, and we're going to have to replace it with a weighted version of it. And it turns out that there is quite an elegant way to add arbitrary likelihood terms to your model. And that thing is called pm.potential. And pm.potential works in a very similar way as your regular model components do. So they take some kind of they need a name first of all, and then rather than having like parameterizations for specific distributions, what it has instead is a function or like a way to compute a likelihood term, a log likelihood term to be exact. So we could replace this line, this pm.Bernoulli line with observed data, that actually can be directly replaced with using the dist version of our Bernoulli with a certain probability p, and taking the log probability of our released data. So rather than initializing a Bernoulli object with a name and a probability here, what we do is we take the dist method from the Bernoulli distribution, which allows us to just ask like what is the log probability of certain data, even when we're outside of a model context. And the only thing that we now actually need to do to make this weighted is to take our sample weights and multiply them with the likelihood from this Bernoulli distribution to make sure that certain samples are going to be weighted more heavily than others. Once again, we can put this in our benchmark. benchmark the balanced model with our data to see whether this impacts the results in any way. And when sampling is done, we see the following appear. Our traces once again look perfectly fine. Same as before, no flat spots, no warnings in the sampling process, no divergences, none of those things. And actually, when we look at the parameterizations and the weights that the model found, as well as the metric that the model found, this seems to make a lot more sense than what we had before. Because of that sample weight, it's now much closer to what we had in the scikit-learn version. And now that we have a comparable benchmark, both in PyMC and in scikit-learn, what we can go ahead and do is try to alter our model to include a constraint, this fairness constraint. And there's a bunch of different ways in which we could do that. But let's start with, once again, copying our previous model and calling it a hard constraint model. Because we're going to try to hard constrain the fairness of this model somehow. And one of the ways in which we could do that is by maybe saying that predictions for both of the classes, for both classes of the sensitive attribute, shouldn't be very different. By, for example, saying that the average prediction for both of our classes shouldn't be very different. And what we can do to get that is we can make two separate data frames. One where the sensitive attribute color is true, and one where the sensitive attribute color isn't true. And we're going to select from our original data. We're going to select both where where color is 1, the observations where color is 1, and the observations where that isn't the case. And given that we have these data frames, something that we can do is we can actually make predictions for the individual classes as well. So we copy this line. We probably don't even need the sigmoid. We can basically say our predictions for our color sensitive attribute true is going to be the intercept plus the dot product between x of color and weights, and the same thing we do where the sensitive attribute color is false. And there's now a sort of difference between means that we can do here by saying we have a deterministic variable, which is the difference of means, which is going to be our predictions for our color group minus the ones where that's not the case. And if we would go ahead and sample this, because it's deterministic, the results of this mudiff will end up in our trace, and we can see what the actual mudiff is going to be. And this is a way in which we could somehow measure a kind of fairness of our models here. The thing we now set out to do was actually to see whether we could put a prior on this mu difference. Whether we could add prior knowledge to our model that says this mu difference shouldn't be higher than a certain given threshold. And it turns out that we actually already know all of the components that we need to do this. Because this pm.potential, which added the arbitrary likelihood to make sure that we could have balanced classes, can also be used to add arbitrary likelihood that this mudiff shouldn't exceed certain values. What we could, for example, say is that we add a potential that is basically our sort of fairness constraint that says that the mudiff shouldn't exceed a certain range of values. And that certain range of values can, for example, be modeled by using a uniform distribution. So what we can say, for example, is that the log probability of observing a certain mudiff is based off of a uniform distribution with bounds minus 0.1 and positive 0.1. Which means that as long as mudiff is between those bounds, it doesn't actually impact our model, but anything that results in a mudiff that's outside of these bounds is suddenly completely infeasible, has a zero likelihood. And we can try and run this using our benchmark function again to see what will this hard constraint model do when we feed it actual data. It turns out that this model actually fails rather spectacularly, Because already very early on in the sampling process, PyMC throws an error that says, bad initial energy, please check any log probabilities that are infinite, minus infinite, nan, or very small. And basically what PyMC3 is trying to tell us now is that for the initial, for the starting point of a trace, the actual likelihood is already minus infinite. And it's very likely that this is caused because of this mutif being outside of the ranges of our uniform distribution. Because there is zero likelihood outside of the bounds of the uniform distribution, PyMC can't sample in that space. And it is rather likely that a starting point will end up in a space that is outside of the bounds of this distribution. So what we can do to maybe solve this is, rather than making this a fully hard constraint, we can try to make it a leaky hard constraint, in which we say, please add a very small likelihood outside of the bounds of this uniform distribution. And something that we could do, for example, is say, well, let's add a maximum around whatever comes out of this uniform distribution, so that if it's minus infinite, if the log likelihood is minus infinite, please make it like a very tiny number instead. And we can try and sample this. And by making this change, we do see that the model samples. We got all the draws that we want. We don't get any particular exceptions thrown at us, but we do see that there are a lot of warnings. And the one that stands out most is this number of divergences. A divergence basically means that the sampler wasn't able to properly explore a certain part of the space. And any kind of divergence in your sampling process is probably a good indication that there's something probably wrong with your model. Also, when we look at the actual trace plot of this, we see that there's a lot of stuff that goes wrong here. Our traces definitely don't look like fuzzy worms anymore. And all of these rug plots we see in the bottom are where possible divergences have occurred. So apparently this isn't a great solution to our problem. But let's first try and see what a divergence actually means. Basically, when PyMC3 goes to sample the posterior from the posterior of your model, it uses some kind of physical analogy. And that physical analogy is that of a particle that doesn't have any friction, that tries to move continuously through the space of your parameters. And basically, if there is a high increase in likelihood towards a certain direction, the particle sort of picks up speed into going into that direction. To actually make it possible to run that sort of physics simulation on a computer, the step size of the particle is discretized. And there are some properties that PyMC3 keeps track of under the hood to basically see if that simulation is a proper simulation and that there's no kinds of errors sneaking into the model. And one of the causes for those kinds of errors could be that the step size is too large for this certain spot in the parameter space that it tries to explore. Basically meaning that wherever the particle was predicted to be is very far away from where it actually ended up to be. And if we think about this uniform, this hard constraint model, what it does is it keeps all the likelihood within the bounds the same, and then there's this super sudden drop-off. Whereas the likelihood of our parameters is very likely to point into the direction of these bounds. So you're always going to have like a very steep drop-off at some point, and that is something that these samplers can't actually deal with all that well. So when it ends up at the edge of the cliff, PyMC3 predicts that the particle will move in the same direction, whereas the likelihood actually says, no, it should drop to 0 here. So if we want to actually solve this and be able to draw properly from the posterior of our model, we probably have to think about ways in which we can make sure that the likelihood already starts decreasing the closer our particle gets to the bounds of our constraints. So rather than picking a normal distribution for our model, a uniform distribution for our model, we're probably going to have to pick something that slopes down towards the edges, like a normal distribution. And there are some disadvantages to this. Because when we pick a normal distribution, we can't really say that we have any hard constraint on our model anymore. but that is going to be necessary for us in order to be able to sample from it. So what I'm doing here is I'm just getting rid of that leaky bit because we won't actually need that anymore. And instead, I'm just going to put a very, very tight normal distribution bound on this mu difference potential. And once we do this, we see that the results are actually much more to our liking. Our sampling looks fine again. We don't get a lot of warning thrown at us. We don't have any divergences anymore. And the trace plot, once again, looks properly fine. But also, we see that the demographic parity score went up quite significantly when you compare it to our non-constrained version of the model. Even though we added the very tight normal distribution on this difference though, we do see that the actual mu difference that the sampler came up with is very far away from these bounds. So even though the standard deviation is 0.01, the mean of the mu diff is around 0.14. And that is quite a big difference. And to actually put like a hard constraint on this is therefore going to be quite difficult using just this normal distribution. And that's a bit of a bummer, because like a soft constraint is nice and it nudges your model into the right direction. But being able to say my model never does X or Y or Z is also kind of powerful in and of itself. Something that we could maybe do though is use this normal distribution to nudge our model into the right direction, and then apply another trick to get rid of all the samples that actually break the constraint. Because for each of the samples in our trace, we could figure out what is the mu diff at this point actually. And if that mu diff is above a certain threshold value that we can define, we could simply say, let's get rid of that sample and not use it when we go and make predictions anymore. And in code, that process would look something like this. We'll define a function called trace filter. And this trace filter is going to take the trace that we want to filter and then the threshold value for the mu difference that we still want to keep and the mu differences that we don't want to keep. And we'll first make a mask, a bit mask that indicates these samples don't exceed the threshold values and these do. So we'll take a look at the absolute value of the mu diffs and compare that with our threshold values. And then the thing that this is going to in the end return is a pm.backend.base.multi-trace object. That is sort of the multi-trace, the regular trace of PyMC3 when you do multi-core sampling. And we're just going to add like a list of one single trace that we still need to go and make. And this new trace needs a couple of things. So we'll say that it's just an ND array backed trace, and there's a couple of things that it needs. First of all, it needs a model, and it needs the variables that it has in the trace. And we can quite easily get them from our original trace. Model is strace.model, and we'll do the same for the var names. Vars is strace.vars. And this strace is just something that we'll get from our original traces. So this new strace is currently completely empty. So we're going to have to add some samples to this. And these samples we can simply also take from our original strace, but then only use the samples where the mask is true. So we'll say varname for varname in trace.varname. So we'll make a dictionary of each variable name, and then the trace, take the original trace, take the varname out of it, and apply the mask on top of that. So we're making a dictionary with the variable names that we traced as keys, and then the values are going to be the original values, but only those selected where the mask equals 1. So where the mu diff is smaller than our threshold value. We'll need to add those samples to our new S-trace, and we need to add another couple of arguments to this new S-trace, like how many draws does it have, which is basically how many ones do we have in the mask. What should the draw index be if you want to add new draws, which is the same. And what is the chain of this new S-trace, which we can just set to 0. What we can now use this trace filter for is, for example, to take the last soft constraint model and apply the trace filter to it with a threshold val of, for example, 0.14. And when we look at this trace plot from the soft constraint model, what we expect to happen is that all of this likelihood, where the mu diff is bigger than minus 0.14 or smaller than minus 0.14 actually, is all gone. So let's take a look at what a trace plot of this resulting trace looks like. And indeed, we see that that is exactly what happens. We notice some slight differences when we compare it to like our previous trace plot. And part of that is caused because this is actually 6 different traces, and here we only stored it as a single one. So that's why all the lines are single lines at this point. But the expected behavior did indeed occur, right? Our mu diff now is always bigger than minus 0.13, the threshold value that we set here. And that means that we can now take our hard constraint model again, and basically, in this trace, add a trace filter to it. We'll say trace is trace filter of our original trace with a threshold val of 0.13. When we benchmark this, we expect that the demographic parity score should increase once again because we now added a hard constraint back to our model. And when we look at the results, we see that that is exactly what happens. The normal distribution pushed the mu diff into an area that's already more closely to the constraint that we set to it, and then the trace filter actually got rid of all the samples that didn't exactly adhere to it. And by doing that, our demographic parity indeed once again went up. And there's a couple of reasons why we're actually really excited about this idea. Because the approach that we have here is relatively generic. We can make hierarchical models, and we can have all kinds of flexibility in how we want to define fairness. You start with a constraint, you translate it into a potential, and you apply a strict filter on it, and that is our general recipe. So what we have here is an approach in which our potential represents some kind of fairness. And because we filter the trace, we have an algorithm that has actually properties that we kind of like. There are, of course, some valid points of critique to this approach as well. Even though we put a hard constraint on our model, this doesn't guarantee fairness in the slightest. We've only guaranteed fairness on a single definition on our training set. And there is merit to this approach, but we should not assume that only doing this is enough. Our dataset in production might drift, and there are other facets of fairness that might be hard to capture using this recipe. In any way, we think that machine learning practitioners nowadays probably spend too much time just optimizing a single metric and should probably spend more time thinking about and adding constraints to their model. And we hope that by using what we've shown to you today, you become inspired to think about constraints to add to your own problem and think about ways in which you might be able to add that during the model fitting process. Because the act of thinking about constraints immediately makes you stop and consider the problem you're actually trying to solve before you even start modeling. And that has a lot of potential.